Hello friends at Physics with Friends. I presented something that was pretty half-baked the other day, the differential geometry session, and I wanted to bake it slightly more. So these are not really carefully thought out ideas, they're just the way that I think about the connection, and I'm exploring some new avenues that I haven't explored before. In particular with the sphere. So I hope people find this helpful. So we're talking about differential geometry, and we see that derivatives get promoted to derivatives plus an affine connection term. And together we call those things the covariant derivative, denoted nabla. And the question is, what the heck is this thing doing? So, first of all, let's talk about this thing. Derivatives. They generate something. They generate translations. So, to start out with, let's exponentiate the derivative. The derivative is an operator. It turns functions into other functions, and the second derivative operator also turns functions into other functions. So there's a third derivative operator, a fourth derivative operator, and what I mean by this exponentiation is the Taylor series of differential operators. This is the nth derivative operator. It turns a function into the nth derivative of that function. Let's go ahead and do it. We're going to put a function here. And so what I'm going to do is convince you that what's happening here is that the exponentiation of the derivative translates. And in particular, I'm going to put a number, xi, there. Xi is just like another form of x. And if I put that there, then it should appear here as well, xi to the nth power. Okay. So what you see on the right-hand side here probably looks to you like a Taylor series of some function, and you might think that it is a Taylor series of the function f, but it's not quite that. We can see that whatever this thing is the Taylor series of, it is centered at x. So it's not centered at xi. Now this thing over here is not of the form something minus x, so that right now is not centered at x. We can make it that by just replacing xi with xi plus x minus x. So that is the same thing as xi, and I just rewrite everything, having just re-expressed xi as xi plus x minus x. Now I have the nth derivative operator acting on the function. So now I have the center, both here and here. And what we see is that I have the Taylor series of the function f of xi plus x. So this thing is an operator, right? It's the sum of the first, second, third, fourth, fifth, all the order derivative operators with different coefficients. And its net effect is to translate by this parameter here. So before I flip the page, I'll just address this word generate. If we have a small parameter epsilon up here, then this is approximately 1 plus epsilon d dx, right? And we ignore the epsilon squared, epsilon third terms. And the idea is that this is, the whole thing here is an infinitesimal transformation, but only part of that thing, this thing, is the generator of that infinitesimal transformation. Okay, and that generator is also here. So you can do an infinitesimal transformation, or you can do a macroscopic transformation. Up here, e to the xc d dx is a macroscopic translation operator. This one down here is an infinitesimal transformation. So if I put in f of x here, then I could say on the other side that this is, let's see, pardon the clutter here, this is going to be f of x. So distributing, that's 1 times f of x plus epsilon times the derivative, let's say f prime of x. And that is approximately f of x plus epsilon, right? If you were to expand f of x plus epsilon, it would look like that. It would be just 1 plus epsilon times the derivative operator. That's an infinitesimal transformation. That's an infinitesimal translation down here. But up here, that is macroscopic. So by xc, I mean not an infinitesimal thing, but a large thing. Okay, so having established that the derivative operator translates, what does that connection do to augment this transformation? What else is happening besides translation when you have a connection in your covariant derivative? So let's talk now about what it means to exponentiate the covariant derivative. Again, with some parameter c, this will be a transformation generated by the covariant derivative. And I should say that this is only going to make sense if this thing is constant. So in general, you'd have to do this, okay? Kind of looks stupid because the derivative thing should probably be all the way to the right. But if you're going to act on some function, put a v here. I want to act this time on a function that is not a scalar, but a function of the coordinates x. In general, you know, the connection is going to change as you go along some path. So maybe it should be like gamma for some path. But if the connection is constant along that path, then you can just put that covariant derivative up there. All right. That caveat aside, let's think about what e to the xc d dx plus xc gamma is all about. We're going to have it act on a vector. And like I said, under this assumption that the covariant derivative is constant, we can break that up into two parts that are this part, which we already talked about and is a translation, and then this part. Okay, so if gamma is constant, if the connection terms there are constant with respect to this derivative, then these two things, they are both transformations, and they're going to commute if the derivative of gamma is 0. Okay, so if they commute, then I can do this. I can say this thing hits that and doesn't do anything, and hits that and translates. And we're left with the action of e to the c gamma. So the derivative translates, and the connection generates something else that is not translation. It is the transformation of the components of the vector, or more generally, the tensor that we're interested in. So in a particular direction, gamma, maybe I should call it a direction like, I'll just call it phi for future's sake. Gamma subscript phi, the connection in the direction of phi, is a matrix. And it's going to have one high index and one low index is a matrix. That serves as a generator. Serves as a generator. A generator of something. So let's work towards having an example. Okay, so we need an example. So we'll go to page 3, and we'll use the example of a sphere. The reason I'm using this is because Guidry, on, what is it? Page 153. Page 153 gives us the metric, connection, and curvature and everything for a sphere. And in particular, anywhere on the sphere, let me try to anticipate using some color. This right here, well, I should probably talk more generally about the coordinates for a second. So if this is the North Pole, this coordinate right here is theta. Wait a minute, that should have gone to the center of the sphere. This is a drawing mistake. There we go. That angle is theta. Okay, and then for this point here, that is the angle phi. So that's really, really small, but we'll say that this point over here is at theta phi, and I hope you guys are familiar with that. It's this polar angle and azimuthal angle. In the direction of increasing phi, Guidry tells us that our matrix has the following components. And I'm going to erase that cotangent just so we can get started with the expression that's good for calculation. Cotangent is cosine over sine. Okay, so that is the matrix for the affine connection in the direction of increasing phi wherever you are on the sphere. I drew this one point that is really, really badly. Let's see. At the coordinates theta phi. Anywhere on the sphere that you are, the connection has these components. So the idea is that as you move along some path, maybe from here over 2 here. You're moving from one theta value to another. So what I should probably do is erase this and say that what I'm going to do is I am going to go from this point, theta phi, I am renaming, to this other one, theta phi plus xi, right? So we're going to travel along this path where we change only the coordinate phi, but not the coordinate theta. Along that path, the connection looks like this. And along that path, e to the xi gamma, the xi is there because that's the coordinate change on the path. Is the exponentiation of that matrix. And that means it is the following Taylor series from n equals 0 to infinity of xi to the n over n factorial gamma to the nth power. Okay, so we need to calculate the nth power of this matrix, and actually it ends up that that's not too hard. I completely botched it when I presented to Physics and Friends the other day. So let me try a little bit harder this time. Let's figure out what gamma squared is. Just to be concise, I'm going to make the components just be SC for sine cosine, and C over S, 0, 0, negative SC, C over S. So multiplying, we've got negative SC times C over S. That is C squared with a negative sign, cosine squared. The off-diagonal elements are 0, and the other is like this. Okay, so then we have negative cosine squared times the identity matrix. Interestingly then, we have that gamma to the third power is negative cosine squared times gamma. And gamma to the fourth power is gamma squared squared. That's cosine to the fourth power times the identity matrix, right? Just the square of that guy. And the rest of these guys are pretty easy to compute. So let's move to another page and talk about what that exponentiation is. E to the xi gamma. Okay. As you can see, the terms that have even powers are going to be just multiples of the identity matrix. And the terms that have odd powers are going to be something times gamma, right? So gamma to the fifth then is C to the fourth gamma. So what I'll do is I'll split apart into the even and odd terms. So this one will be the even terms. And over here, I'll put the odd terms. Both are indexed by n, so what I mean is the terms over here have the even values of n from the other page. Heck, I should probably do something like this. K, right? So when k is 1, it corresponds to the n is equal to 2 term from over here. Okay, and then we'll have xi to the 2n. And then we need to put in the 2nth power of gamma. Okay, the 2nth power of gamma. We get a cosine squared every time that we take a square. Okay, so we get cosine to the 2n for the 2nth power. And then we actually have that -1 floating out in front. -1, and this is to the nth power because it's actually every 4 terms that, or I should say k. Okay, sorry. I will try to be consistent with n's and k's. And then the identity matrix goes right there. Okay, and then for the odd terms, we get something very similar. flipping around between pages. So there's the -1 to the nth power. And we'll get cosine times c to the 2k plus 1. Sorry, this should be a k. Remember, these are the odd terms, so we're looking at the 2k plus 1 factorial terms. But actually, that's too many cosines. There's actually only 2k cosines in the 2kth term from the previous page. So we need a 1 over cosine to get that guy back in there. And then we have a gamma on the outside. Okay, and I will just write in what gamma is. It was 0, 0, negative cosine sine and cosine over sine. This 1 over cosine will just, I'll do it by erasure, knock out these guys. And notice that outside of this parenthesis is constant, right? This does not change with k. And similarly, the identity matrix does not change with k. The thing that's inside of this parentheses is cosine of, I know it looks ridiculous, but cosine of theta, that's the c here, times c, right? So that goes across the diagonal. Okay, and then here on the anti-diagonal, we have this sine times whatever that is. This here is the cosine, or sorry, the sine of cosine theta c. Okay, and then we've got that thing on the outside, over here, a negative sine of theta. Okay, and then on this component, we have the same sine of cosine of theta times c, but this time divided by sine of theta. Okay, so that is the exponentiation of gamma in this case. What is that thing doing? If you squint, you've got cosine, cosine, negative sine, sine. This is roughly speaking the rotation matrix, but it's going to change with the parameter c, and it certainly depends on where you are on the sphere as far as the polar angle. A rotation. It's not a rotation. Rotation would have to be cosine of something, sine of something, cosine, cosine, negative sine, sine, but you can see that it doesn't quite work out perfectly. A rotation matrix. That depends on theta and c. Remember that c is the amount that we change the coordinate phi. Okay, so that is to say, where were we? 3, this is page 4. Going back to this idea, let's see, I want to do page 5. E to the c nabla, in this case, when it is in the direction of phi, acts on a vector in two ways. It has the derivative part, and it has the connection part. And I guess I'll write those as separate exponentiations. Acting on v. The first term changes v of, I shouldn't say x, well, instead of x, I should say theta phi. Changes that to v, the vector field, evaluated at theta and phi plus xi. But we have not yet applied e to the xi gamma. That is a matrix that we just calculated. Right? It is a matrix acting on the components of V at this point. Okay. All right. So, interestingly, we can keep going with this. Let's see, I would like to draw not the sphere itself, but this is the North Pole. If I draw a line of constant theta and changing phi, I'd like to draw the overhead view of this. I have learned that when you draw a circle and something in the middle, you should draw the circle first and then draw the point in the middle later. It's easier. So I always get that backwards. Okay, so this is the overhead view. And what's happening is we're translating the point theta phi with a vector at it over to the point theta phi plus xi. Right, and we're moving across that path. Maybe I should make the path in purple since it starts with a P. Right. The path is oriented, it's pointing that way. So if we start out with a vector here at theta phi, we could do something like, let's see, what's a good one? Go. So how about this vector? That, in this picture, would correspond to, pointing out this way, it is theta hat, which, since we ordered the coordinates theta and then phi, this would be 1, 0. Okay. All right. So what on earth should we do as we move over here? The idea is that we're going to apply the matrix E to the xi gamma to those components, theta hat over there at, maybe I'll say at the initial, right? That's going to turn into something else. Just looking at the matrix on the other page, multiplying 1, 0 by that matrix, that's going to give me cosine of theta times xi, sine cosine of theta times xi over sine of theta. In particular, thinking of theta here as pretty small, so I'm thinking of this red circle of constant latitude being pretty close to the North Pole. That's going to make this 1 over sine quite large. Okay, that second term was 0 here, but it has become non-zero. Right? So this blue thing got transported over here, and it does not point in the direction that is theta hat, not at point naught, but let's see, I'm a final. I could do like initial. Okay, so this vector is not that vector. it gets changed by this operator e to the C gamma. It gets changed so that now its phi component is, it's stated its phi component, its second component is going to be large. Okay, so instead of only pointing outward, it will also point somewhat in the phi hat direction, right? So that's like the final point right there. So phi hat f. It points a little bit in this direction and a little bit in that direction. And in particular, I'm going to say, since I'm thinking of theta as being quite small, we'll do this. Okay. So this is that arrow. Okay. The operator e to the C gamma picked up this blue vector, brought it over here, and it has different components. Okay. I'm at 30 minutes, so I'm going to go ahead and call it on this video. I hope this is helpful to some people. I have some other ideas about how to explore curvature out of this too. One thing you can do is you can say, this is not a geodesic, but there is a geodesic that does this. My handwriting's getting bad because I'm rushing. And if we follow this path, the non-geodesic purple path, and then the blue path, geodesic path back, then we will rotate our black vector or our blue vector here into the green vector and then rotate again. And that is how curvature is calculated. It is the way that a vector changes as you move in a loop, right? So we can extend this example to explore the curvature on the sphere using the connection that Guidry gave us, you know, if there's demand for it. So let me know. Thanks for listening. It's been fun.